Oh, hello. Hey guys, hello.
Hello. Go turn on this light.
Yeah. I see more people coming in, and probably get started at 8 o'clock, maybe 8:01.
Hello? Wait, can you hear me?
Yeah, I can hear you.
So Chloe is in another class right now, and I'm her sister. So can I record this class for her until she joins?
Yeah, I'm gonna record it, and I'll
Okay.
post it on YouTube after class. So
Thank you
yeah.
so great.
Hello.
Hello. Yeah. I'm just here in this class with a bunch of names. Very nice. I'll probably wait a little bit longer for anyone else who might want to come in. Maybe one more minute and then I'll start.
What's the username?
你进来干嘛？ Okay, so I'm just gonna get started now. Share my screen with everyone. Can everyone see my screen okay? Anyone?
Yeah, we got it.
Yeah. Okay, cool. So, welcome to physics. And what is physics? Well, I'm sure most of you have some kind of idea of what it is. Physics is basically the study of motion, and like everything that you can see around you, physics is acting upon it. So we're gonna do motion, forces, gravity, all that kind of stuff. But first, we need to start this week with the basics. And we're gonna start with one-dimension kinematics. And if you're not sure what that is yet, I'll describe that later. Let's get started. So today's topics, we're going to be talking about, first we're going to talk about reference frames. We're going to talk about reference frames, and then after that, we're going to talk about distance, velocity, and acceleration. And lastly, we're going to be talking about the kinematic formulas. And as you can see, I've got these three formulas here, and you don't need to write them down right now, and I'll be explaining them later in class. Okay? So let's start with reference frames. Let's start with the most basic idea here. Let's just say I'm here and I'm running at 10 miles per hour. Well, what does that actually mean? Most of the time when we refer to speed, we're referring to speed relative to the ground. Okay, so I'm going 10 miles per hour relative to the ground. And if I had, let's just say I had a friend in front of me who was also running at 10 miles per hour. Well, relative to him, I wouldn't be moving at all, right? So relative to my friend, my speed is 0 miles per hour. So all speed is relative. And this is really important when we're doing physics, because when we're calculating our speeds and our motion and our forces, we have to keep the reference frame the same. For example, I can't compare my speed to ground 1 minute and then I compare my speed to my friend. I have to keep that the same. Okay, so let me give you another example here where there's a moving train and the train is moving forward at, let's just say 20 miles per hour. And we have a man inside who's walking forward at 5 miles per hour. Well, relative to the train, the man is moving at 5 miles per hour, but relative to the ground, he's moving at a far greater speed, 25 miles per hour. Right? So it's all the speeds are relative. We have to keep this constant when we're doing our calculations. Another thing that's important in physics is that we establish a positive and a negative direction. So in physics, when we're talking about distance, we can have positive distance and negative distance, okay? And what that basically means is that if I move 5 feet in one direction, that means moving negative 5 feet is moving 5 feet in the exact opposite direction, okay? In physics, we do have negative and positive directions, and we have to establish that before we do any calculations, okay? And you can switch these out whichever way you want. For example, I could have set my positive direction as this way and my negative as this way, and if I move this way, I would be moving in the positive direction. But the thing is, just like reference frames, we can't change these things. We have to keep these things really constant throughout our calculations. All right, so those are basically the things that we have to keep constant when we're doing physics. Let's first talk about speed versus velocity. So most people think that velocity is just a fancy word for speed. Well, this is not true at all, okay? Velocity is not equal to speed. one thing, if I'm talking about speed, speed has no direction. What does this mean? If I'm saying that I'm going at 25 miles per hour as a speed, then I'm just going at that speed. I don't know which way I'm going. And just like my example with positive and negative, if I'm going at 25 miles per hour, I don't know if I'm going in the positive or the negative direction. On the other hand, velocity has direction. And velocity is what we call a vector. We're going to use vectors in physics, but you're also going to use this in pre-calculus. Okay, so vectors are basically a fancy word for something with magnitude and direction. As in speed, we only have magnitude, but with velocity, we have a direction. For example, if I were to have positive 5 feet per second, well, that would be positive. If I have a negative velocity, then I'm moving in the opposite direction. So the sign of the magnitude on velocity tells me which direction I'm going in. Okay, but with speed, we can't do that. I can't go at negative 5 feet per second as a speed. That's just not possible. So that's the difference between speed and velocity. And another difference between speed and velocity are their definitions. Velocity, which we're going to use a symbol V for, is just displacement over time. And speed is length of path traveled over time. Okay, for example, if I were to have point A, point B, okay, and what's the definition of displacement? Displacement is basically my beginning point, my end point, and I'm going to subtract the distance between those. Okay, so velocity only depends on my displacement. For example, if I were to move from A to B in 10 seconds in a straight line, that would be, let's just say that's V, okay? If I were to go in a really squiggly path that's a lot longer than the first, but I still get there in 10 seconds, it's the same velocity, okay? So velocity only cares about my beginning and my end point. We compare those two distances, and whatever that is, we take the velocity. On the other hand, with speed, speed is the length of path traveled. So if I travel a longer path, I'll have a greater speed, okay? And so, I have a practice problem here. I have a circular track of radius 10 meters. All right, if I go all the way around the track, go all the way in one circle, can you guys calculate what is my velocity and what is my speed? Give you like a minute to figure this one out. If you have an answer, maybe you could just say it out loud. But I don't think I can look at the chat right now. Yeah, I can't see the chat. So if you have an answer, you can just turn on your mic and say it.
Well, if velocity is about displacement, then you technically haven't gone anywhere at all.
Yes, correct. So velocity is displacement. My starting point is right here, and my ending point is the exact same place. I haven't gone anywhere in terms of displacement. So I have zero displacement over time. That's 0 meters a second, right? For speed though, I'm going all the way around the circle, and my path traveled is 2 pi r, right? So
Yes, 10 pi.
it's going to be 20 pi over t. So this is my speed. So as you can see, we can clearly see a difference between our velocity and our speed in this situation. So in physics, we're mostly going to use velocity. Okay, let's get into velocity and acceleration. So what is exactly the definition of velocity? Well, we just defined it, right? Displacement over time, right? And we can rewrite this as triangle x, or delta x over t. So the triangle is basically the Greek letter delta, which means change. And x is position. Like on the x-axis, for example, if I were to have x equals 3 and x equals 5, right? So this is the change in position over time. That's basically what displacement means. We can also rewrite this as some x minus an initial position over time. okay? Or we could just write d as displacement over time. And I usually like writing this, okay? And what is acceleration? I'm sure many of you have heard of acceleration before. Acceleration, by definition, is the change in velocity, the rate of change of velocity. So for example, if I'm driving my car, like I can't drive yet, I'm too young. But for example, if someone was driving their car and they press on the gas and they go faster, well, they're changing their velocity, so they have an acceleration. Well, the same thing goes for when they press on the brakes. Is that still acceleration? Well, yes, it is. Acceleration is basically any change in speed. It doesn't matter if it's going faster or slower, it's just the change in velocity. That's all we care about, okay? So even if he's pressing on the brakes and slowing down, that's also called acceleration, okay? And just like velocity, acceleration has a direction, okay? Let's just say I have a negative here and a positive here. If I have a negative acceleration, my acceleration is going to point this way, okay? But if I have a positive velocity at the same time, what does this mean? My acceleration is counteracting my velocity, so I'm going to slow down, all right? What if my velocity was also in the negative direction? Well, then I would be speeding up, right? Because my acceleration is adding velocity to my velocity at this moment, okay? So basically the cool thing is that if acceleration is in the opposite direction of velocity, you're going to have to slow down. You're going to be slowing down, okay? And if your acceleration is in the same direction as velocity, you're going to speed up. So the actual definition of acceleration is, again, change in velocity over time. And you write this just like what we did with position. I'm going to have some v minus v0 over time. Okay, so this is the definition of acceleration. And what are the units we're going to use with velocity and acceleration? Well, for velocity, we're going to have meters per second. And for acceleration, well, I think many of you have memorized that it's meters per second squared. But why is that? Well, we have velocity, which is meters per second, over seconds, because this is the rate of change of velocity. So we basically have meters per second squared. So these are the units we're using for acceleration and velocity. Okay, and a common form of acceleration that we all know is gravity. Like if you take a Lego and you drop it, it's gonna fall, right? Because the Earth is pulling stuff towards itself. So we have acceleration due to gravity. Okay, and this rate is the exact same as long as you're close enough to the surface of the Earth. Okay, and after scientists did a lot of testing, we have found that the acceleration due to gravity, g, is 9.8 meters per second squared. Okay, so this is a number you should memorize. Okay, so whenever an object is falling, it's accelerating downward at 9.8 meters a second squared. Okay, and we can also prove this value with physics. I'm not going to talk about that today. Talk about that sometime later. Okay, so now with our definitions of velocity and acceleration, let's try to solve these problems. All right. So maybe you can take a few minutes to solve this problem. Oh no. What just happened? Okay. Take a few moments, just try to solve this problem here. It's two problems actually.
For the second one, it should be 10 seconds.
Okay, we'll talk about this in a few minutes. Uh-oh. Computer's doing something weird. everyone done?
Yeah. Yes.
So, looking at this problem, I have a distance, 1 meter, and a time, 1 day. But the thing is, we can't just plug these values into our equation just yet, because 1 day, if you note, 1 day is not in seconds, because our velocity has to have units in meters per second. Right? That has to be true. So we have to turn this 1 day into form of seconds. Well, let's just calculate how many seconds there are in a day. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. That is 86,400 seconds, okay? So now we got everything. Well, meters is already in, so 1 meter, okay? So now we can just plug these values into our equation for velocity. So our displacement is 1 meter. Velocity equals displacement over the amount of time it takes, 86,400 seconds. Velocity is therefore 1.16 times 10 to the negative 5 meters a second. Okay?
But wouldn't
You
that
get that?
depend on which direction the snail is moving? If it just moves 1 meter in a circle, wouldn't it not be displaced at all?
Well, when we're talking about velocity and in physics, we're still talking about displacement, okay? So the 1 meter, it's not the length of the path it travels, not necessarily. The 1 meter is its displacement, okay?
Oh.
But 0.1, it's at, let's say x equals 0. And that after 1 day, it's at x equals 1. So because of the way velocity works, we can just plug these values into our equation. And the next one is a little simpler. We have everything in the units we want, right? Okay, so therefore our velocity is 100 meters a second and our displacement is 100 meters. Okay, so 10 equals 100 divided by t. And t equals 10 seconds. All right. Uh-oh. Let me try to share my screen again. You guys see my screen?
Yes.
Okay. Some technical issues here. Uh-oh. Okay, next slide. So now we have acceleration. So let's do some calculations with acceleration. I'll give you a few moments to do these problems here. There's a typo right here. Whoa. Okay, so is everyone done? Anyone? Anyone done? Okay, so let me explain the first problem here. So we have an acceleration here, 3 meters per second squared. So we can put that right into the equation. And now we have change in velocity on the top. Well, what is our change in velocity? Remember, change in velocity is our final velocity minus initial velocity. Okay? So what is our final velocity? 67 meters a second. Initial is 10 meters a second. So our change in velocity is 57. Okay? That's being divided by time. Okay? Now if we solve for time, we'll have time equals 19 seconds. Okay? Now the second one. Bob is moving left at 9 meters a second. If his acceleration is 2 meters a second squared to the right, how long will it take until he's moving to the right 17 meters a second? Okay, so this is one of those problems where I have to establish a positive and a negative. You could do positive on the left and negative on the right, but I'm just going to do it this way. Okay, so Bob right now, he's moving left at 9 meters a second. That's his V0. That is his initial speed. Okay, its acceleration is 2 meters a second squared to the right. So that's a positive. Okay, that's a positive acceleration. How long will it take until he's moving to the right? At some point down here, he's moving to the right at 17 meters a second, so he's going in a positive direction. Okay, so let's plug these values into our equation. So we have a positive acceleration, 2, equals change in velocity, which means our final velocity, 17, minus our initial velocity, -9. Okay, so that's pretty complicated right there. So as you can see, this is why it's really important to write out this diagram and establish our positives and negatives. And we're dividing that by time. So if we take out our calculator, time should be 13 seconds. All right? That shouldn't be too difficult, shouldn't it? All right. Uh-oh. Let's go to the next slide. So now we have some more complicated formulas here. This is the first of the kinematic formulas that I was talking about. This is the equation for average velocity. And something I need to set right now is that acceleration is going to be constant. In physics and even really advanced physics, I don't think you're ever going to work with something where acceleration is not constant. At least it's really rare to see that. And after acceleration changes, then it gets really, really confusing and a lot of weird stuff happens. So we're going to assume that acceleration is constant. So what does this mean? If we draw a velocity versus time graph, that means if we start at some v0, the velocity is going to steadily increase. Steadily, 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 until we get to some v, final v, right? So what is the average velocity we have? Well, by intuition, we're just going to draw a dot down the middle. So then the average velocity would be the mean between the initial and final velocities. So remember what mean is? Mean, median, mode? I think you might have learned that in 5th grade or something. So the mean would be the sum of these two divided by 2. So this is the average velocity. How are we going to denote average velocity? This v with a dash in front of it, okay? And remember our equation for v equals d over t, displacement over time? Most of the time, we're going to be working with average velocity, okay? So in this equation, velocity is actually the average velocity. But since we're working with constant acceleration, we can just assume that the velocity will be the average velocity in like basically any of the equations we use, okay? So most of the time, we just don't write that dash in front of it. We just write the general v, okay? So if we combine these two equations and set these equal, since they're both equal to average velocity, we're going to find that v plus v0 over 2 equals d over t. So displacement will equal to t times v plus v0 over 2. And this is a formula you might want to remember. Okay, so this formula relates our displacement with time and our initial and final velocities. Are there any questions? Okay, maybe I'll give you a second to write this one down. Okay, let's move on. So now we have this formula. We can do some problems with it. Just in case you didn't write it down, let me write it again up here. So we have our average velocity equal to v plus v0 over 2. And our distance will therefore equal to v plus v0 over 2 all times time. Okay, maybe I'll give you a few minutes to work on this. Yeah, maybe if you want to have, if you have the answer already, maybe you can just private that to be. So we want to give everyone a chance to solve the problem themselves.
0.
Maybe if you have an answer, just privately chat that to me because I can see it now. I might not be able to apply to everyone's, but if I don't, then it's probably being correct. It's probably correct. Okay, is everyone done?
Yes.
Okay, so I think everyone did relatively good with the first problem, as we just plug these values into our equation here. Bob starts out at -3, so that's our initial velocity, and he ends up at 3, so that's his final velocity. Dividing that by 2 to get our average velocity, 0. So how far has he gotten this time? We can basically plug our value for average velocity into this equation, and we get d equals 0t. So it doesn't matter what time it took for him, he has gone nowhere, because anything times 0 is equal to 0, okay? For the second problem, we had a little more issues here, okay? So let's take in the information we have. We have 38 meters in this time, so his displacement is 38. So we're gonna be using this top formula right here. Plug that in, and he ends up at 18 meters a second. So his final velocity is 18. All right, and we want his initial velocity, so we're going to plug that into our equation here as a variable, dividing that by 2 and multiplying by 9 seconds, and we just solve this equation here. So let me just solve it up. 38 divided by 9 times 2 minus 18. Initial velocity, negative 9.56 meters per second. All right. What does this negative mean? Well, if we assume that he's going positively, and let's just say it's going this way as a final velocity, that means in the beginning, he was moving left at 9.56 meters a second, okay? That is his initial velocity. So that's what the answer actually means. So if you get a negative answer for velocity or acceleration or distance, don't worry, that is supposed to happen. All right, let's go on. Now we have a second really, really important formula here. Very important. So this formula will link time, distance, and acceleration together for us. Let's start out with the definition of acceleration. Acceleration is the change in velocity over time. In other words, velocity minus initial velocity over time. Okay? If we rearrange this so we have acceleration times time equals v minus v0. I'm going to add v0 on both sides to get v equals v0 plus at. Okay, so I'm going to add v0 to both sides of this equation. We're going to have 2 v0 on this side now, right? And I'm going to multiply each side by 1/2 t. Okay, and now let's distribute the t on this side of the equation. And I get v0t, because the 2 times 1/2 equals 1, plus 1/2 at squared. Okay, what about the left side of the equation? This looks wildly familiar to our equation for distance, right? Displacement. Remember equation 1? So this is the exact same thing. So this is actually our displacement. And this is the formula. Really, really important. Because this is about the only equation that will link time with velocity, acceleration, and displacement. Okay, so the problems associated with this problem are going to get a little harder. Okay, associated with this formula are going to get harder than the first one. Okay, because now we have 3 variables. Wait, actually 4 variables to look after. Okay, so I'll give you guys a moment to write this down in your notebooks. All right. So let's do some problems with this. Okay. If you forgot to write down the formula, I'll just write it down here again. Distance equals initial velocity times time plus 1/2 the acceleration times time squared. It'll give you, say, until 8:40 to do this one. Maybe earlier if you can do it just a little faster. If you have an answer, please chat me and I'll tell you if you were correct. Uh-oh. Don't think I can see that. Please round your answers to the nearest hundredth. Maybe the nearest tenth, depending on what the situation is. Okay, so that is time. Do you guys need some more time to do the problem? More time, no time. Should I explain them? Is anyone stuck? Remember, when you have an answer, please privately text the chat me in the chat. Maybe I'll wait one more minute. These things are actually kind of hard. Yeah, we're going to be doing 2D motion next week. Well, no, it's not. It's not moving in 2 dimensions. It's just going straight up and straight down. Okay, so I'm just going to explain them right now. So, for this problem, we only have one value given to us. So what are we going to do? Let's first look at the first part of this problem here. How long does it take for the ball to land back in my hand? Okay, so let's visualize it. The ball is going up, coming back down in my hand. So what is its displacement? It's actually gone nowhere, right? Its displacement is 0. Okay? And the value that's given to us is its initial velocity, 10. And now, what is A? Remember, everything on Earth is under the influence of gravity. So right now, I've established that my positive velocity is going up. So the positive is up and negative is bottom. Okay? So acceleration due to gravity always pulls things down, right? So the acceleration is going down. So the acceleration must be negative. And if you remember, the acceleration due to gravity at the Earth's surface is negative 9.8 meters per second squared. But remember, it has to be negative because it's going in the negative direction. This is why it's really important to establish your directions. Okay? Now let's solve this for t. I can factor it and get 10 plus, wait a second. Wait, I gotta undo this. Minus 4.9 t's, okay? And obviously 0 can't be a solution to this equation, okay? So we have 10 minus 4.9 t equals 0 and t 2.04. All right? Let's move on to the next part of the equation of the problem here. How long did it take for the ball to reach its maximum height? Well, we could plug this into the equation here, but let's take a smarter approach. It takes 2.04 seconds for it to go up and come back down, okay, right? So intuitively, it takes half the time to go up and half the time to go down, and that is absolutely right. So it takes half the time for the ball to go up and down to go just up. So we're just going to divide t by 2 to get the other t is 1.02 seconds, okay? And now, what was that maximum height? Well, we could use this again. But let's not remember our first equation here, which was distance equal v plus v0 divided by 2 times time. Right? This is a lot simpler than the equation we have right here. And we know that the time it takes for it to get up to its maximum height, we already know that, it's 1.02 seconds. And we also know the initial velocity. But what is the final velocity? Well, any object, when it's at its top, it's not moving anymore. So the final velocity must be 0. So now in this equation, we have everything we need to solve for d, right? So d equals the final velocity, 0, plus the initial velocity, 10, divided by 2 times 1.02 seconds, okay? So distance is 5.1 meters. We could have solved this with this complicated formula right here, but we always want to take the easiest route to solve these problems, because oftentimes on tests, you don't have that much time to solve problems at your own pace. So you want to use the fastest method possible. Okay? Let's work on this problem now. This is really similar to the last one. Let me write the equation again. Right? Maybe I'll give you, I don't know, 4 minutes. If you do it, tell me the answer that you got. So again, it's really, really important to define your positive and your negative directions. Okay, so now I'm going to go ahead and explain this problem. So basically, I'm throwing up a ball from 1.5 meters from the ground. All right? And throwing the ball up at some initial velocity v0. Okay? And the ball hits the ground 3 seconds later. So after 3 seconds, it goes kadung, 3 seconds, hits the ground. Okay? So let's take a look at what we have here. We do have v0, which is, we don't have v0, so that's what we're trying to find. But we do have time. Time is 3 seconds. And we do have our acceleration, which is g. Now let's first define our positive and negative. I'll do that. And so our acceleration will be negative in this case. Okay? Negative 9.8 times 3 squared. Is everyone with me? And what is our displacement? The important thing here is that the ball is actually going down. Its displacement is going down, so its displacement is negative. Okay? This is why it's really, really critical to draw out this diagram and define your positive and negative directions. Because the ball starts out at some height, and in the end, it's on the ground. So it's dropped lower now. Okay? So now we're just going to solve this equation for v, and in the end, v0 should be 14.2 meters per second. Okay? Move on to the last thing I'm going to do today. We have a third really, really important formula, and this one is my favorite formula. And I think it's one of the best ones. And so this one relates our velocity, distance, and acceleration. So I'm going to start out with the definition of distance with equation 1, right? V plus V0 over 2 times time, right? If I multiply acceleration on both sides of those, okay? Let's look at AT right here. Well, what is AT? Well, this reminds me of the equation acceleration equals difference in velocity over time. So instead of writing AT here, I can write V minus V0. And I'll move this 2 to the other side first, 2AD. All right? Now let's expand this guy out. And difference of squares, we're going to have V squared minus V0 squared equals 2AD. And therefore, if I move V0 to the other side, V squared equals V0 squared plus 2AD. And this is a very, very important formula here. Okay, I'll give you a second to write this one down. Okay, let's do a problem with this one. Wait a second. If you don't memorize these right now, it's totally fine. If you do enough problems, and I'll send out some homework later. If you do all the problems, then you'll get these basically in your mind pretty easily. So I'm gonna write out the formula again for you guys. Right? Okay. So it looks like we only have time for one problem right now. So I'll give you guys 5 minutes to do this one, and please chat me, private chat me the answer if you get one. Now, just to clarify, at the bottom, that means that the ball is going to hit the ground. Okay, so instead of bottom, I can write ground. So when it's about to hit the ground, what is its speed? And that's the same for all of these prompts here. Okay, I'm going to go ahead and explain this problem. So I'm at the top of a 50-meter tall building. This guy is 50 meters tall. And first I'm going to define my positive and negatives. So this time I'm just going to go positive on the ground, negative in the sky. Okay? So this way my displacement will be positive. If I drop a ball down, how fast will it be going at the bottom? So if I drop it, I'm dropping it, so my initial velocity, if I drop an object, that has 0 speed, right? Because if I just drop it, I'm not throwing it or anything, it's just dropping. Okay, so my V0 here will be 0. Okay, and we're trying to look for our final velocity. So we're just going to plug this into our equation. 0 squared plus 2 times acceleration. So what is our acceleration? Is it positive or negative? Well, g is going down, right? So, and since I've defined my positive as on the ground, then my acceleration will be positive. And my displacement will also be positive, 50. Solving this equation, your answer should be 31.3 meters per second. All right. So now what if I threw the ball down at 10 meters a second? Well, then the only thing that changes is my V0, right? Because if at the top I throw it down with initial speed, that only changes my V0. Instead of having V0 as 0, I'm going to have V0 as 10 right here. Okay? So that's literally the only thing that changes. And calculating this, I should get 32.86. All right. What if I threw it up at 10 meters a second? Well, that means if it goes up, it's going in a negative direction. So it must have negative velocity if it's going up. So all I'm doing is that I'm turning this 10 into a negative 10. See how that goes around the parentheses? Because negative 10 is V0, and I'm squaring that value. So I'm squaring negative 10. Okay? If we do the math, we have 32.86 again. What does this mean? If I throw the ball up at 10 versus throwing it down at 10, at the end, we get the same speed at the bottom. So what does that mean? If I throw a ball up, let's just say I'm at the top of the building right now, throwing it up at 10 meters a second. When it comes down, it's going to cross this point again, right? And at this situation, it's going to be exactly like the second prompt here when I'm throwing the ball down, right? And that must be the same because I got the same answer as my final V. So we can have the cool conclusion here that whenever I throw an object up at some speed, it will come down at the exact same speed. All right. So let me stop share here. And now I'm going to summarize all the formulas that we've learned. Okay, so first we have the definition of velocity. Change in position over time, or x minus x0 over time, or displacement over time. Okay, and what is the definition of acceleration? Change in velocity over time, v minus v0 over time. Okay, and then our kinematic equations here, we have average velocity equal to final plus initial divided by 2, and our distance is therefore equal to final plus initial divided by 2 times time. Okay, and now we have a complicated formulas. We have distance equals v0t plus 1/2 at squared. And also we have v squared equals v0 squared plus 2ad. Okay, so take a screenshot, write this down in a notebook, as these are the formulas that you'll need to know. And if this seems kind of hard and new to you, don't be scared, because as long as you do more problems, you'll get more fluent with these formulas, and you'll get better. So that is it. And next class, we'll be talking about two-dimensional kinematics, and I'll see you then. Have a good night.
Thank you.
Bye.
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 Thank you.
Bye.
Thank you.
Thank you. Bye.
Bye.